Hi everyone, my name is Cameron and today we're going to be looking at the using of our resources from the earth. So we're going to be looking at rusting, we're going to be looking at useful alloys, the properties of some of our man-made polymers and natural polymers, glass, ceramics and composites, the Haber process or the Haber process, however you want to pronounce it, the economics of that process, as well as how we're going to be making fertilizers in the lab. Okay, so let's start with corrosion. So when it comes to corrosion, it's going to be caused by a chemical reaction between a metal substance and the environment. Okay, a lot of the times it's usually from the oxidation of that metal substance. Okay, so what's going to happen, for an example, is iron, oxygen, and some water are going to react to form this hydrated iron oxide. And that is what rust is. That's that brown stuff, is rust. Okay, it's going to be oxidized iron. Now to prevent rusting, what we can do is usually coat our metal in a sort of insulator, okay, to protect it from water and air exposure. So this can either be by paints. You get some non-rusting paints that you might see on handrails. Another one would be oils or greases, plastics, a less reactive metal, as well as sometimes a more reactive metal. Now when we talk about this more reactive metal, what we're talking about is sacrificial metal. This is metal that is more reactive than the metal we care about, and therefore it's going to be the one that oxidizes and rusts instead of the metal we don't want rusting. A lot of the times you can see this at the bottom of ships and anywhere where there's going to be constant exposure to oxygen and water, but it can't be coated in something else. We'll then use the sacrificial metal. Sacrificial metal obviously has to be replaced or cleaned then. So a metal alloy is when we're going to mix metals together to give it different properties. Usually what it's going to do is make the metal stronger. Okay, so when it comes to bronze, bronze is going to be a mixture between copper and tin. Mankind used it for hundreds of years. Okay, and a lot of weapons and a lot of armor was made out of bronze for many years. Okay, and the fall of the Bronze Age of man was catastrophic because bronze became very scarce. Okay, brass is made out of copper and zinc. We're going to mainly use that for musical instruments. Aluminium, there's many aluminium alloys. So when we look at an aluminium can or we look at aluminium foil that you might cook with, it's not going to be pure aluminium. It's going to be an aluminium alloy. Okay, gold, same thing. We don't use pure gold for our jewelry. Usually what we're going to do is we're going to mix it with something like copper. Okay, so if something is 24 karat, it's the closest to 100% that you're going to get. If you divide the carat number by 24, you'll get the fraction of how much gold there is in the jewelry. Okay, so 24 karat gold divided by 24 to 1, it's going to be 100% gold. Okay, and then steel alloys also, it's going to be iron and carbon. Okay, so iron is pretty strong as a metal. Okay, but what adding carbon to it is going to do is make it a lot harder, but it also increases how brittle it becomes. So that's why you can take iron and bend it a lot easier than you can something like steel. Okay, but then yes, it becomes a lot more brittle. Okay. Okay, so properties of polymers. So we know from our previous lesson that polymers are going to be created by monomers, okay, being put together. And a lot of the time it's from products of crude oil refining. Okay, so our less useful, less fuel-like products of crude oil we're going to be making into these polymers. Okay, a lot of the times it's just plastics. So for something like polyethylene, you can have two different types. We can have low density and high density polyethylene. So low density polyethylene is going to be used when there needs to be a bit more flexibility, okay, such as your plastic packets or something that doesn't have to be rigid. Whereas your high density polyethylene is going to be a lot stronger, a lot more rigid, and going to be a lot more resistant. Okay, so how it's made, using very high pressure and traces of oxygen, ethene molecules are going to, ethene monomers, let's say, are going to be combined to form polyethylene, low density polyethylene. Okay, what's then going to happen is we're going to use a catalyst, heat up that low density polyethylene, and increase the pressure to make high density polyethylene. Okay, so high density polyethylene again has a higher softening temperature and stronger than that low density polyethylene. Okay, so your pipes, as well as containers, okay, that need to be rigid, they're going to be made out of high density polyethylene, whereas your plastic packets, things that don't need to be so strong, can be made out of low density polyethylene. Okay, so now we're going to be looking at glass, ceramics, and composites. So glass, we all know, it's that see-through, transparent, hard material that we use for our windows, for cut or crockery, you know, for your glasses to drink out of. Okay, but what is it made out of? What is glass? Okay, so glass is going to be made out of sand, limestone, and sodium carbonate or soda. Okay, this is the most common form of glass, is this soda lime glass. So the raw materials are going to be heated to 1500 degrees Celsius. This is going to melt them and join them together. So they react to form this substance, this molecule called glass, okay, and then it's going to cool and solidify with a non-regular pattern. Now what are they talking about? When we talk about a non-regular pattern, something like quartz has a regular pattern, whereas glass has a non-regular pattern when its molecules are going to cool and join together. Okay. Now ceramics, okay, this is a hard substance. We usually use ceramics for something like pottery, toilets, sinks. Okay, it's quite hard but very brittle. The materials are also used as electrical insulators. Okay, a lot of the times for power lines we can use ceramics to prevent them from short-circuiting with rain. Okay, they are made of molding clay into the desired shape, and then we're going to heat it up to about 2000 degrees Celsius in a kiln. Okay, that's going to kind of cure it and make it strong. The clay contains compounds of metals and non-metals. Okay, and finally composites. This might be something you haven't come across before. Composites are going to be made up of two different things. We're going to have a matrix, which is going to be a binding agent, and we're going to have binding fibers, okay, of a different material. So we can't have the matrix, okay, it's going to be like a liquid. It's not going to have the it's not going to have the desired properties, okay, and the binding fibers as well, they're going to be too loose. But if we put them together, we can make a material such as fiberglass. So this is something that we're able to mold to a certain shape. It becomes very hard afterwards, but they're also very lightweight. Okay. Other composites, of course, include something like concrete. Okay. So when we take concrete, it's going to be made up of cement powder, okay, as well as some rocks and some sand, and that becomes a very hard substance called concrete. Okay. Okay, so most of our fertilizers are going to be containing something called ammonium nitrate. It's very good for plants and plant growth. Okay, but this contains nitrogen. So the Haber process provides a way of turning this nitrogen from the air into useful ammonia. Okay, usually this is done by bacteria, but when we're talking about our large-scale crops, we're going to need some help. Okay, the bacteria can't keep up with our demand, so that's why we have to create these nitrogen-based fertilizers. And although nature does it in a small bacteria cell, we require incredibly big factories and quite a dangerous process to do the same thing. Okay, so how does it work exactly? We are going to take nitrogen from the air. Luckily, our atmosphere is something like 70% nitrogen. We're going to then take hydrogen, usually from a natural gas such as methane. Okay, and what we're going to do is first purify the nitrogen and hydrogen, and then we're going to pass it over a very hot catalyst at 450 degrees at a high pressure. And what's going to happen is ammonia will form, but this is a reversible reaction. Okay, so any unreacted nitrogen and hydrogen will just be recycled back into the process, and eventually we'll have refined ammonia. Okay, so there's the chemical formula for it. Nitrogen plus hydrogen in the presence of this iron catalyst is going to give us ammonia. Okay, but that ammonia isn't the final step. So it needs to now become useful for the plants. And what we're going to do this is we're going to take about 70% of that ammonia made in these factories, and we're going to add nitric acid to it and form ammonium nitrate. Okay, and this ammonium nitrate is what we can then use as fertilizer. So solid fertilizers can be made by reacting this ammonia with different acids. So it can either be nitric acid or it can be sulfuric acid as well as phosphoric acid. Okay, so these are all neutralization reactions, and what comes out is very healthy for plants but extremely dangerous. Okay, so a lot of the times you can go look up, fertilizer factories can blow up and cause huge devastation because it is a very volatile substance. An example of such an explosion was the explosion in Beirut in Lebanon back in 2020. Okay, that was ammonium nitrate that was being kept in storage and then exploded and wiped out, I think, something like 2 kilometers of buildings. Okay, so it's a very dangerous process, and it has also been used for car bombs and terrible things before, but a lot of fertilizers now don't use as much ammonium nitrate, okay, because people were just buying it for evil purposes. Okay, so I hope you've learned something today, and I will see you in the next lesson.